Given two strings text1 and text2, return the length of their longest common subsequence. If there is no common subsequence, return 0. We'll review our first example. A subsequence of a string means the characters stay in order, but we can skip some in between. A common subsequence is just one that shows up in both strings. The longest common subsequence in this case is ALO, and so the answer is 3. Here is our second example. The longest common subsequence is BE or CE, and the answer is 2. There may be multiple valid answers, but they'll all have the same length. Let's see how this works. We place two pointers I for text1 and J for text2. If the characters at I and J match, we count 1 and move both pointers forward since we found part of the subsequence. If the characters at I and J don't match, we have two options. First option is to skip the character at I and move to the next in text1 while keeping J fixed, or skip the character at J and move to the next in text2 while keeping I fixed. In both cases, we then compare the rest of the strings. Notice that both options are just smaller versions of the original problem. We explore both and return the maximum of the two results. For our base case, if either I reaches the end of text1 or J reaches the end of text2, that means one of the strings is exhausted, and so we return 0. We define the recursive formula for LCS of I and J like this. Next, we'll walk through the code which directly mirrors this formula. This is our base or stopping condition. If the characters at index I and index j match, we call the LCS function recursively on I plus 1 and j plus 1. Otherwise, we explore both options recursively, skipping a character from either string and return the maximum result. The time complexity of this approach is O of 2 raised to the power of m plus n, which is exponential. This is because we make two recursive calls at each step. The space complexity is O of m plus n. Now, the LCS for these two strings that we reviewed earlier is ACE. Let's visualize how the recursion tree unfolds. Do observe that the recursive call with indices 3 and 2 repeats. These are overlapping subproblems. We are solving the same subproblem multiple times. On larger strings, overlapping subproblems increase quickly and slow things down. Memoization helps by caching results and skipping redundant work. Let's review the code. We create a dictionary called cache. We create a unique key using the current indices I and j. If we've already solved this subproblem, we just return the cache result. After computing both options, we store the result in the cache before returning it. The time and space complexities of the memoization approach are both O of m times n.